In the finite element method, structural bars are traditionally modeled using the simplest possible geometric assumption. The baseline element is defined exclusively by its two endpoints. When we apply immense physical tension to a structural member, the internal material deforms and warps along its entire length. The standard two-node computational model assumes that the physical displacement between those two endpoints follows a strictly linear path. But a straight line cannot accurately capture the true internal stress distributions of complex loading scenarios. Physical reality involves localized strains and variations that linear interpolation ignores. The geometric solution is straightforward. We insert a third data point, a new node located directly in the center of the element. With 3 points of reference, the predicted displacement field morphs from a rigid straight line into a continuous parabolic curve. Mathematically, we have transitioned from a first-order linear model to a second-order quadratic interpolation model. Shifting from 2 known values to 3 increases the element's internal accuracy, but it requires solving for a higher number of mathematical unknowns to define the element's behavior. Engineers rely on 2 primary strategies to increase computational accuracy in finite element analysis. The first is the H method, which refines the physical mesh by dividing the structure into hundreds or thousands of smaller, standard 2-node elements. The alternative is the P method. Instead of modifying the physical mesh, we increase the polynomial order of the existing elements. By utilizing a higher-order polynomial, the model maps continuous structural variations mathematically without increasing the total number of physical pieces in the simulation. The major drawback is the algebra. Deriving these higher-order equations by hand requires tedious matrix calculus, introducing a high probability of human error. The modern engineering solution bypasses manual calculation entirely by utilizing symbolic manipulation software. A symbolic computation engine takes the core rules of structural mechanics and automatically processes the required calculus, outputting clean, programmable mathematical variables. By offloading the algebraic heavy lifting to symbolic logic, we can algorithmically derive the exact stiffness matrix for our 3-node element without touching a single manual equation. The first computational step is defining the structural interpolation function, known as H. For a 3-node element, H takes the form of a row vector containing 1, x, and x squared. Because the element has 3 distinct nodal displacement values to interpolate, the mathematics dictate a second-order polynomial with exactly 3 terms. To evaluate how the structure resists force, we must find the mechanical strain, which is the spatial derivative of the physical displacement. We instruct the symbolic software to take the spatial derivative of our interpolation function with respect to x. The resulting variable, h subscript x, acts as our new strain interpolation vector. We now possess the abstract mathematical rules governing displacement and strain. To make them useful, these abstract variables must now be mapped directly onto the physical geometry of a specific structural element. We transition from the abstract polynomial to the specific spatial coordinates of our 3-node bar. To build the necessary geometry matrix, the interpolation function h must be evaluated at 3 exact nodal locations. The first geometric point is the start of the bar, where x equals 0. The second point is the dead center, at x equals L over 2. The final point is the end of the bar, evaluated at x equals L. This resulting 3x3 grid is the transformation matrix. It links physical nodal coordinates to the abstract polynomial coefficients. To relate the internal displacement field back to the nodes, we must solve for these coefficients. This requires inverting the matrix, a critical step that allows us to eventually link nodal forces to displacements through a single stiffness matrix. While this matrix inversion is the primary computational bottleneck of the P method, it is necessary for translating local geometric coordinates into a global framework. We reach the final assembly phase, combining the strain vectors with the inverted transformation matrix. The core mathematical operation required to find stiffness is taking the dot product of the transposed strain vector and the original strain vector, multiplied by the inverse transformation matrices. The symbolic software integrates this dot product over the entire physical domain of the bar, from 0 to length L. The solver generates the precise numerical output, a 3x3 grid with rows of 7, -8, 1, then -8, 16, -8, And finally, 1, -8, 7. Notice the exact diagonal symmetry within the resulting stiffness matrix. These specific integer weightings, 7, 16, and -8, are the direct mathematical results of integrating a quadratic curve. By bypassing manual calculation entirely, we guaranteed an error-free exact solution for these coefficients. With the mathematics verified, we can transition from isolated algebraic theory back to macro-scale engineering applications. This single high-accuracy component can now be replicated thousands of times. By mastering the algorithmic derivation of a 3-node element, we possess a high-order mathematical building block ready to be deployed into complex global trust systems.